good morning, everyone. I hope you can hear me. First of all, thanks a lot to Gottfried and Justice for keeping up the presentation despite this big troubles in the internet connections. And thank you, Michael, for the kind introduction. Today I will present our work on a plastic pollution budget. The presentation will mainly cover the technical aspects, but I will link them to some aspects of political governance also. The work was part of the plastic budget project from 2017 to 2021 and funded by the German Federal Ministry of Research and Education. The project partners were the Ruhr University Bochum and Fraunhofer UMSICHT. The goals of the project were to conduct source and quantity determinations for plastic emissions, the development of a plastic pollution budget, the integration of plastic emissions in life cycle assessment, and participation and governance through this three steps. I will deal today with the first three topics only. The history of plastic production is a success story in just 70 years. If we consider thermoplastics and thermosets as well as man-made fibers and rubber, production has increased from almost zero to about 470 million tons per year. The cumulative total production already reached over 11 billion tons in 2020. But at the end, it is a success story, but you can't make an omelette without breaking eggs, or as we say in German, wo gehobelt wird, da fallen Späne. The production, use and end of life of plastic is associated with emissions. First of all, there's the question what we actually mean by plastic emissions. There are numerous difficulties of classification here, which are discussed both in science and industry. This is as much about founding new fields of research and science as it is about rejecting responsibility for environmental problems. In a broader sense, it would make sense to include all anthropogenic emissions of polymers, regardless of whether they are natural, modified, or synthetic. Even natural fibers, if they are taken from one environmental compartment and enter another compartment, can cause negative environmental impacts if critical quantities are exceeded. Nevertheless, our work so far has been limited to plastic emissions that are solid at room temperature, which is marked here in the figure in red. We use a broad definition of plastics that also includes elastomers and man-made fibers. From an environmental point of view, this makes sense and is important. In particular, there are lots of discussions surrounding the definition of microplastics. From an environmental perspective, the exclusion of nanoplastics makes little sense. And the upper limit of 5 millimeters, although widely accepted, is also arbitrary and cannot be justified, either physically or environmentally. In the end, such limits are more likely to lead to regulatory gaps than to advance in the environmental subject. We therefore use the term plastic emissions without any size limits. Plastic emissions are manifold. A few years ago, we thought mainly of exfoliating particles in cosmetics and pellets on the Mediterranean and North Sea coasts. In the meantime, however, we have discovered a variety of emission sources, some of which are very large, for example, tire abrasion, weathering of outdoor paints, filling material of artificial turf fields, foils in agriculture, but also coated seeds or fertilizers, the impression mask at the dentist, or the cutting of a lawn trimmer. Sometimes we even ingest plastics voluntarily as a capsule for medicine. And even if we make an effort to sweep up all the plastic emitted, we should remember that the bristles of the broom are made of nylon and abrade during use. What's about the quantities? Until now, there are only a few studies with rough estimates on plastic emissions available, including our own for Germany from 2018. The most detailed studies have been prepared for Scandinavian countries. When we compare the studies, it's important to consider what is reported. Are losses reported, which originate directly from the application of plastics, or final releases to the environment? To make it short, for Europe, however, it can be stated that the emissions that are not directly removed at the point of origin amount to about 1 kilogram macroplastics and 3 kilogram microplastics, in total 4 kilograms per capita and year. While the focus in the media is primarily on visible plastic litter, it can be said that this is only the tip of an iceberg. Within the framework of our project, we have developed two tools to quantify and assess plastic emissions: a plastic pollution equivalent, which is particularly suitable for the labeling of products or as an impact category in life cycle assessment, and the plastic pollution budget, from which threshold values for countries, individuals, industries, or organizations can be derived. The plastic pollution equivalent is defined as the sum of all emissions from a product, process, or service that enter an environmental compartment multiplied by the residence time in this environmental compartment and related to a reference residence time. The PPE therefore has the unit kilogram, or more precisely, kilogram plastic pollution equivalent. As already mentioned, there are a multitude of sources that need to be taken into account. There are currently a number of players in industry and science who are trying to bring a little more clarity into the darkness. At Fraunhofer UMSICHT, we have so far mainly dealt with tires, agricultural inputs, and artificial turf pitches. The data situation must still be described as uncertain. What we do see, however, is that the first publication on emissions are generating a certain amount of pressure, especially to industry, so that we are increasingly gaining more insights and better data. A special problem is littering, where we have to estimate what is not captured by cleaning processes. Here we lack good methodological approaches so far. It is like asking a policeman how many murders are actually not detected, and you will never get an answer on this. The data situation for transfer rates is also still very insufficient. So far, we have mainly relied on expert statement and few measured values. The table shown here divides plastic emissions very roughly into 3 groups and uses density as the main criterion for dispersion or distribution from an entry compartment to a final compartment. It would be good if we could model and simulate the transfer in the future. However, physical data is required for this. At Fraunhofer UMSICHT, we are currently determining the wind speeds at which plastic particles start moving in practical tests. Size, density, and the roughness of the surface play a crucial role here. In addition to the determination of quantity and transfer rates, the residence time within an environmental compartment is the central quantity with which we weight the emission. The residence time is derived by the degradation time. We have therefore evaluated a large number of scientific literature that have dealt with degradation in real environmental compartments. From these literature, we were able to determine environmental and substance-dependent degradation rates. From these, further on, we can then estimate the lifetime. And from the lifetime, we obtain the residence time, with size and shape as further important variables in the calculations. The residence time is given by a rectangle equal in area to the degradation curve and corresponds to something like a full emission equivalent time. It is common in the evaluation of environmental effects to give limiting time horizons for the period under consideration. A common value is 100 years, which corresponds to about 3 generations. Anything beyond 100 years is out of our scope of responsibility and even imagination. As a result, for very slowly degradable plastics, we could reduce our experimental efforts and set the residence time at 100 years, which makes it much easier, especially for polyolefins. An important parameter for the plastic pollution equivalent is the reference time. We have set it at 1 year. This means that all plastic that is present in the environment for a much longer time will receive a much higher PPE value. The PPE value can be interpreted as a virtual mass or as a mass rucksack backpack caused by the persistence on the material. It is expressed in kilograms, analogous to the greenhouse gas equivalent. I have listed here some examples which are rough approximations, but not unrealistic. For example, driving of a car for 1 year leads to emissions of 1,650 grams natural and synthetic rubber, or to 16.5 kilogram PPE. This is very much, for example, compared with sanding of 1 outer door, which only leads to 0.5 kilogram PPE. Nevertheless, extensive use of a lawn trimmer, for example, yields also significant PPE, and littering of 10 coffee-to-go cups has nearly the same PPE like driving a car for 1 year. And I think this is an interesting result. I said that the PPE can be interpreted as a virtual mass, but while we used 1 year as a reference time, there's a second and more physical interpretation possible. The PPE is also the hold up of an emission which results over a longer period of time if the practice continues in the same way and reaches steady state. By this, we can derive the plastic pollution budget based on the accepted hold up of plastic in the environment. It then is equally to the annually acceptable PPE. I will show it once again in this figure. The annually emitted mass of plastic is transformed to a plastic pollution equivalent, and this equals to the hold up if the practice continues over a longer period. On the other hand, the accepted amount of plastic in the environment leads to the same value of a plastic budget. And when the PPB is lower than the annual PPE, then measures for reduction are needed. An important question is, what is the acceptable amount of plastics in the environment? A fast answer would perhaps be nothing, but then the complete ban of plastics would be the only opportunity. Therefore, as a working hypothesis, we suppose that the current amount in the environment is just about acceptable. And there are some rough estimates from literature and our own work on what has already been accumulated in the global environment. If we consider that some degradation has already happened, a value of 250 million tons seems reasonable, and we use it for our further argumentation. As explained, this hold up leads also to 250 million tons PPE annually, which are allowed. And if we assume same emission rights for every human worldwide, this leads to 32 kilogram PPE per year. Nevertheless, this acceptable hold up and the share of emission rights has to be agreed upon in future political processes. How much then is 32 kilogram PPE? Driving a car 1 year and additionally littering 10 non-biodegradable cups would already fully consume this budget. As there are a lot of more practices by which plastic is emitted, it becomes very clear that we have to change our way of dealing with plastics. If we assume that the average emission is about 4 kilograms per year and person, as shown in the beginning of my presentation, and if we furthermore assume a typical share of polymers, where most of the polymers are hardly degrading polyolefins or vinyl polymers, the second big group are natural and synthetic rubbers, which are somewhat medium degradable. The third group are little degradable polymers like nylon or most polyesters, and where easily degradable plastics plays only a minor role, below 1%, then we can calculate the plastic emission to be more than 215 kilogram PPE nowadays in Germany, which is 6 to 7 times the set plastic emission budget. So we need some scenarios how to reduce. Here I have given some of the scenarios, and in principle there are 2 ways to reduce. using better biodegradable plastics, or directly reducing the emission. If we shift to better biodegradable plastics only without reducing the emission, this will not be enough. And if we reduce the emission only, but not use biodegradable plastics, we will also fail to reach the plastic pollution budget. Nevertheless, if we combine both strategies, we will perform well. In a more balanced scenario, where we reduce the emissions by 2/3 and increase the use of biodegradables to 1/3, we exactly reach the set PPB. Nevertheless, this remains a challenging goal for the future anyway. What is shown by the scenarios is that we need better biodegradable plastics to manage the problem. But by no means this should be used to justify higher emissions. Biodegradability therefore has to be understood as an emergency characteristics rather than giving a reason to thoughtless environmental open uses of plastics or even littering. Nevertheless, I'm convinced that if we accept that every human activity will lead to an emission, then a circular plastics economy, which is discussed a lot during these days, has to be based on better biodegradable plastics. To come to an end, what can a PPE and PPB be used for? A PPE can be used for product labeling, for example, making decisions between different types of tires, clothes, or paints. It can give you an information about the impact of littering and gives pressure to better biodegradable alternatives, and perhaps it could be used as a base for a pollution-depending fee, for example, in the German dual systems. It can also be integrated in LCA, what has been comprehensively described in an article we just published in the Journal of Life Cycle Analysis last month. And of course, the PPB can be used to define reduction potentials or targets for nations, branches, companies, or individuals, like it is already done for other environmental impact categories. If we compare the situation in global warming and plastic pollution, we have to face the reality that both are challenging in the same magnitude, what is shown here in the figure on the down our right side. What do we need? In future, there's still a lot of work to be done. We need more accurate data about losses, transfer paths, and rates, as well as better degradation test or simulation tools, especially for hardly degrading plastics. As mentioned in the beginning, the framework should also include soluble polymers, modified natural fibers, paper, viscose, or cotton, because they also can cause environmental problems if they are entering environmental compartments where not originated from. And of course, a political initiative and incentives are needed to transform the PPE and PPB into measures against plastic pollutions. That would be great. Thank you a lot for your attention and for the possibility to give this presentation here.